So we're gonna roll back to chapter 10 in grade 12, and we're gonna do some composite functions here. So we're gonna determine the composite function of f of g of x. So g of x is gonna be our inside function, and it's gonna replace anything in f of x that is the variable. So for part A, we're gonna have h of x equals 2x minus 1 squared. That would be the composite function of that. We took the g of x function and we put it inside the f of x function. So today with the chain rule, we're going to be doing derivatives of composite functions. And again, it makes it a little bit easier to do the chain rule instead of multiplying everything out of the composite function and doing that from there. So part B says we're going to evaluate when g of negative 1. What's g of negative 1 in the composite function?
9.
It is 9. And you can do it one of two ways. You know what the composite function is, so you could just simply substitute it into here. Because this one works out kind of nicely. Or the other way we did it in grade 12 was we looked at the g of x function and did that. And then we took this number and substituted it into the f of x function. Either way, you're going to get the exact same answer, but I think this was the method that we used more in grade 12. Kept it a little bit different, a little bit separate. This will work, and substituting it in, like both of those are good answers.
Please excuse the interruption. This is just a test for electrician. Thank you.
How did you the first times?
I know.
They could have done it like 10 minutes ago.
They could have done it 10 minutes ago. But what would be the fun in that, Rahat? Okay, so what's the composite function here for h of x? I'll give you a second to put what you think is the composite function together. Chances are you're going to be right. And then if we were to evaluate h of negative 1, we're evaluating this function h of negative 1, so that's going to be 1 over, oh, I feel like we just did this question. So nothing too spectacular there. That's pretty easy, straightforward. So the second page of this, I got to pick up the pace if we're going to get through this. F of x and g of x. So it's saying, hey, this is your composite function. Can you break it down into the f of x and g of x?
No.
What would you say? What is your f of x? F of x being your outside function. Yeah. And what would you say your g of x is? X minus 1. Because if we put those back together, it would result in, if we did f of g of x, it would result in that equation. And we did this for a little bit in grade 12. And people ask, like, how do you know? But it is really just kind of looking at it and pulling it apart. This is where we're going to spend more of our time in the chain rule. You're going to get something like this. If you treat it as a composite function, then we can apply the chain rule to it. So again, if we have f of g of x, and this is our composite function, what would f of x be? cubed, and your inside function, the one you're putting in there, is gonna be 2x plus 1. So again, we're just taking that composite function and we're breaking it down into two parts, but you need to make sure that your f of x is the outside one and your g of x is the inside one. Just keep that stuff in mind. Okay, so what we're going to do today is the chain rule is useful for differentiation of composite functions. So we can simplifying the original function before differentiation. So that's kind of the long way. Or we can apply the chain rule. Sometimes one might be easier than the other. So all it is that if we have a composite function h of x that's made up of an inside and an outside function, the derivative is going to be the derivative of the original times by the derivative of the derivative of the inside function. So it gets a little bit confusing, but again, it's just kind of like that product and quotient. If we keep them separate and we continually go back to the formula, it will get easier as we apply them. Okay. So we are going to do this one. It's the exact same question. Expand, simplify, and then differentiate. And here we're going to use the chain rule. It's the exact same question. We're just going to see that we get the same answer. What are you doing, bud?
My binder exploded on me.
Oh, no. It's not even like, we're not even halfway through the semester and you filled that binder up pretty fast. And it's not even me this time. It's not even me filling the binder.
Usually it's you.
Usually it's me, but it's not me this time. Okay, so we are going to expand. So this is 3x squared plus 1 times 3x squared plus 1 times 3x squared plus 1. So all we're doing is expanding it, and then we're going to multiply, and then we're going to differentiate. So I'm going to multiply my first two together first. So I get 9x to the exponent of 4 plus 3x squared. It's not terrible. It's not what is terrible?
This.
Why is this terrible?
When your binder explodes.
Oh, okay, yeah, that is terrible, no question. I think I did that, right? And this is the danger of the expanding, the multiplying. Like, are you going to remember to do all the terms? Are you going to miss an exponent somewhere? Are you going to multiply them correctly? This one has its drawbacks too. So once we're all to the same place,
And now we do the inverse thing here.
now we do our rules. Now this one's nice and easy to differentiate, right? So h prime and 6 times 27,
162.
162, x to the exponent 5, and 27 times 4,
108.
108, x to the exponent 3, 9 times 2 is 18 to the exponent x. What happens to my 1? It's just a 0, so I don't have to worry about it. Right? Everybody good with that? So there we go. That is my derivative. That's the derivative. So that's one method on how to deal with it. Now we're going to use the chain rule. Okay.
Do we have to use the chain?
Hopefully you're going to find the chain rule a little bit easier. Okay, so let's bust this apart into our g of x and our f of x functions. So what would our f of x be?
X cubed,
X cubed. What would our g of x be?
3x squared plus 1.
Yep. Okay, so we've done that step in breaking them apart, like it's a composite function where f is our outside, g is our inside. And now we're going to do the derivative of f. So that's going to be 3x squared. And we're going to do the derivative of g. All right, so the formula is h of x is equal to the derivative of f of x as a composite function with the original g of x times the derivative of g of x. So that is the format. All right, that was just from the other page. Okay, so we said that the derivative of f of x is 3x squared. But we have to put the original g of x in where we see x into this equation. The original g of x into the derivative of f of x. Holy Hannah. Here we go. So this was 3 bracket, and I put the g of x function, the original g of x, so 3x squared plus 1 squared. Oops, that should be purple. And this is all going to be times by the g of x function. Okay, so here we go. We're going to finish it off. And I can multiply these two together. If that makes it easier, I can multiply front to back. And that would be 18x. I'm just going to leave that out front here. And then I'd have 3x squared plus 1 times 3x squared plus 1. So we get the exact same answer. So I'm not sure which one would be better. I think we all probably feel more comfortable with expanding, multiplying, and then doing the derivative just because that's where our experience is. But if you do the chain rule, we're going to get the exact same answer.
Now that everything's under control, everything seems okay.
Okay. And this is where the chain rule gets great. And we're not going to simplify. Do not simplify. Because this one, if we were to do the expanding, we would have 5 binomials that we have to multiply together. And I don't have time for that. No one has time for that. But if we use the chain rule, it will go a little bit better. So remembering that the chain rule is f prime g of x times g prime of x. Okay, so that is the chain rule. The more you write it down, the more likely it's to be remembered in your brain. But if I were to pull the composite function apart, my f of x,
X is 1.5.
okay, and what's g of x? 6x minus 1. It's the inside function. So if I do the derivative for f of x, if I do the derivative for g of x, and I'm just using my rules from D3 to do this quickly. All right, so now we're going to put it all together. So we take the derivative of f of x, that's our outside function. And anywhere there's an x, I'm going to replace it with 6x minus 1. So I said do not simplify, so you could leave it like this, but I think I just tidy it up. Like I just multiplied those two together just to put the 30 in front, just so there wasn't kind of constants at the front and the back, just to make things a little bit nicer. All right. And we're not going to simplify this one.
DNS.
Yes, DNS. I think I would write this as a negative exponent. I think that'll be easier for applying the rules to. So that was helpful for us in D3. So I think I'm going to do it here in D5 too. So the composite function would be 3x minus 2 cubed, but it would be a negative 3 now. Because I'm just making it a negative exponent, I'm pulling it up to the top. And that would make it a little bit easier. So if I leave it like that, can you guys go ahead and apply the chain rule and we'll see where we end up? Did you try this one, Rahat? You're done? So I think I would accept either of these fully. I think mathematically, what's grammatically correct is always having positive exponents in your answer. But this one here, or this one, would be the exact same thing and they would both be perfectly correct. I think you guys probably stopped here. But you might have a prof or you might find that they say express as a positive exponent only. So then I would just drop that to the bottom.
But you're good with that. So you're good with that.
Yeah, are we all good with that? Did you have y prime?
Yeah.
Did you make sure it wasn't f of x or h of x? It was y prime. Okay, we're going to use one that I rarely ever use, but you're going to see a lot. The derivative of y in relation to t, and t is because it's in here. It's not an x. If this was an x in here, then this would be an x out here. This is the symbol for the derivative of this particular function. Okay, chain rule. And again, I always do these little side notes because it definitely helps me. Oh, that should be f of t and g of t. I think my pen's running out. And so if you made that same mistake and put an x in here, that would be a half mark deduction because you're introducing a variable that's that's not defined. X is nowhere in this given equation. Okay, we're hat. You're on a roll. Keep that roll going. So no primes needed with this particular format. There's no primes needed. And we're not going to simplify this. We're just going to go ahead. And do not simplify. DNS. I know we don't have to simplify, but I always try to get those. If they're easy multiplying, like you got a monomode by a constant or a constant by a constant, I try to get those all together just so it doesn't get too fuzzy, too sloppy.
This seems pretty fun.
It's pretty great.
It's
pretty
not
great.
as bad as like D2. D2 made me want to cry.
It's going to get complicated here. Okay, so now we're applying the chain rule with the product quotient rule. So we're layering on the stuff that we know. Okay, so we would use the product rule here first. So what is the product rule? Anybody remember? No? It would be on your sheet as well. F of x times by g prime of x plus g of x times f prime of x. I'm running out of room. Sorry, you guys can't even see that. So that's the product rule. Okay, so what we need to look at is this guy here is our composite function. So this whole thing is f of x. This one over here is g of x according to our product rule, right? But this one is a composite function, so we need to use the chain rule. So we need to use the chain rule here to find the derivative of f of x because we need that for the product rule. Holy Hannah, it's a lot of stuff. So we know that our g of x function is nice and easy. It's 2x cubed plus 5. So our g prime of x is going to be 6x squared. All right, here we go. So now we're going to apply our chain rule to that highlighted thing right there. So we have f of x is equal to 3x squared plus 2 to the exponent 5. All right, now we can't use f of x and g of x again because they're already being used for the product rule. So I'm going to bust them apart and I'm going to use k of x, and say is the outside function. So that would be x to the exponent 5. And we would then have, I'll say b of x, which would be 3x squared plus 2. We know that the derivative of k of x would be 5x to the exponent 4, and the derivative of b of x is going to be 6x. Okay, now we gotta actually put the chain rule together. So the chain rule, what does the chain rule say? The chain rule says that we start with the derivative of the f of x function, which in this case is our k of x. So that's going to be 5. And then we put the b of x function inside, so 3x squared plus, I got hair in my mouth, 2x to the exponent 4 times by the derivative of the inside function, which is 6x. So holy Hannah.
So this is our real,
So our f of x function was this one. The derivative of the first one is this one. We had to use the chain rule because it's a composite function, but now we got to put it into the product rule. So you've applied the chain rule. Now we're going to go ahead and apply the product rule. And this is where things get confusing. The math isn't hard, but keeping it all straight and everything's called f of x is very difficult. So I don't know if we want in our chain rule to always label them k and b, or if we want to label them whatever your initials are. Maybe the chain rule inside outside functions. I is fine, but O is kind of difficult. Okay, now we're going back to our product rule. So our product rule stated that to find the derivative of the whole thing, like that, the two binomials multiplied together. I guess it's not really a binomial when it's to the exponent 5. Here we go. So the f of x function was 3x squared plus 2 to the exponent 5, and we're timesing that by the g of x derivative. So that's times 6x squared. And I'm going to run out of room, so I'm just going to go to the next line. So then we take the g of x function, the original, 2x cubed plus 5, and we're going to multiply that by the f of x derivative, which we had to use the chain rule to find. So that's this one down here, times by 30x times by 3x squared plus 2 to the exponent 4. And we are not going to simplify that.
simplifying that would be.
It would just be long, and chances are we'd all mess up somewhere in it. If that was the only question I had to do today, I could probably do it. But we have other things on our mind. So you see how it gets kind of cumbersome really quickly when we're applying rules upon rules. Okay. Here we go again. Now we're using the quotient rule, and the quotient rule states, what does the quotient rule state? The quotient rule states,
Is it still better than D2?
really? I don't think so. I'd rather do D2 till the cows come home. We have g of x times by the derivative of f of x, subtract f of x times the derivative of g of x, all over the g of x function squared. Oh, I put that squared in the wrong place. Let me put brackets around it to fix it. There we go. That's your quotient rule. And so what we see, where did my highlighter go? What did we see here? This is a composite function. And so your top would be your f of x, your denominator would be your g of x. So in order to find the derivative,
So first we murder the f of x. And
I
then-
think we don't murder it. I think we find its derivative,
Yeah.
right? Because we know our g of x function is 2x squared plus 4. So if we do the derivative of that nice and quickly, that's going to be 4x. And now we got to do the chain rule for our composite function.
That's just gonna be 3x squared, right?
What?
Wait, what? Oh,
What?
okay.
Oh, I didn't do that right. You're right, it'd be 3x squared, because I didn't even do my derivative of this. Wah. See, if I only had one question to do, I'd be a genius, but doing more than that, I can't be responsible for that.
So now we smash the f of x function with chain rule.
What is up with you and wanting to like destroy, like physically destroy stuff that's never coming back?
Yes, now just chuck it in the chain law.
Might as well chuck in the chain law. I think it's a rule, but not a law. I don't know, but. Okay, did you find it or did you redo it? I wonder where that got to. Okay, thank you for redoing it. Okay. All right. Now I'm going to put it all into the quotient rule, because now I have my f of x function, which was this. I have my derivative of the f of x function from the chain rule. I have my original g of x and so the things I'm looking for, that, and that, right? Those are the four things. The k of x and b of x help me get my derivative for the f of x. All right, now we're going to put it into the chain rule, or the quotient rule. So y prime is equal to g of x original, so 2x squared plus 4, times by the derivative of f of x, which is 36x cubed, 3x to the exponent of 4 plus 2 squared, close my brackets, subtract the original of the f of x, which is 3x to the exponent 4 plus 2 cubed, times by the derivative of the g of x.
Okay, this is our.
Good thing is we don't have to simplify any of this. Divided by the original g of x, but squared. So again, it's like a lot of math.
I feel like calculus is just taking everything we learned over like the past 4 years of high school and like.
Mushing it all into one.
Yeah, like the past 4 years of high school now feel like the first page of Mr. Beck's baby book. And this is like.
Yeah, all those were, yeah, exactly. Okay, so now we're going to look at higher order derivatives. This is a lot of things in one thing. So higher order derivatives, the second derivative represents the slope of the first derivative. The first derivative describes the slope of a function. The second derivative derives how quickly the slope of the function is changing. Okay, so this is what you need to know. The original function. Deals with displacement. So you're finding out how far you've gone, what point it is on the graph. So it's about just the input, the output. All right. So when we're talking about these different levels, the first derivative no, sorry, not acceleration, it's velocity.
Where do you get into physics?
All this is physics, like you're walking through the door to physics. So when we're looking at the first derivative, we're looking at how fast things are moving. So we're looking at velocity. When we look at the second derivative, we're looking at how fast velocity is changing. So that's your acceleration. And when we look at the third derivative, and this is related to a jerk motion.
Jerk motion?
Yeah. So like how fast something moves in a short period of time. So you're looking very quickly. So if I were to grab you by the ear really quick and let go,
Okay.
maybe that'd be a third derivative. That's what I'll just tell your parents. We were just working on third derivatives when I shook them. So the reason why we want to put words with it is because if I asked you to find velocity, I'm asking you to find your first derivative of a function. If I'm asking you to find acceleration, I'm asking you to find the second derivative. And so we probably didn't make these connections in physics, but this is how it's related to the math. All right, here we go. So the displacement of an object in motion is given by this function. Determine the functions that describe velocity, acceleration, and jerk. So we're finding first derivative, we're finding the second derivative, and we're finding the third derivative. So the question's going to be, when you get a question like this, is how do I find that very first level derivative? The very first level derivative you're going to get is going to be super easy, right? This one is a composite function, so we know we have to use the chain rule. So when we're going to do that first derivative, we are going to take my original function, or my outside function. He's going to teach you very similar stuff, but probably you'll be able to do velocity using derivatives if you know this. So, and I think Beck will allow you because he's really good at calc, but you'd have to check that with him. He may want to see it in a particular way, but you could also find the equation for velocity using your first level derivative.
We need a graph, like without we can't find it, or like we need an equation which won't be given. So it's for university level physics.
Okay.
Because it won't be given in the terms of like a function
Mm-hmm.
or a graph, so we need to use like Newton's laws of motion.
Oh, okay. But if you were given a function, you could use your derivatives.
Like that's why calculus is needed for like physics, can engineering,
Yeah.
like all the questions and this, if you know this displacement. and
If you
time,
know the displacement, you
then
can do
find anything.
everything else.
Because math is just.
Math is great. It really is a good time.
And does calculus is it involved in like finance too?
Not so much. Not so much. But your ability to create formulas for situations are going to be huge in business, right? So you're going to have to create a whole ton of equations based on what's happening. You're going to have exponential growth, decay, things like that. You're going to have to use logarithms, like, so it depends on where you want to go into the business stream. If you're doing marketing, maybe not.
I guess it's financial analyst or something like.
Yeah. So we're going to have 4x squared minus 3 squared times 8x. Okay, so we just found the equation for velocity. All right. Okay, so now we're going to go to acceleration. So really, when we're looking at acceleration, I have here a composite function being multiplied by another function. So this is the chain rule and product rule all combined again. Now, you could avoid this if you wanted to by expanding this out and multiplying them all together, because this is only a squared. So maybe you'd feel more comfortable at this point multiplying it out, multiplying those three things together. You could totally do it that way and then use your laws from D3. We're going to practice with the chain rule. You can like that, you can not like that. But let's practice with the chain and product rule. But just know that like this is a squared, so I might be like, I don't trust my product and chain rule together, so I'm going to expand it and then just do my D3 quick rules. Either way, you'll get the exact same answer. Okay. So if I take that first function,
I have no idea. I kind of lost after both.
pardon?
Okay.
What are you lost at?
No, I was like, okay, so got my chart.
So this is the product and the chain rules all together. Okay, so all I'm doing is I'm looking at this one, I'm finding its derivative, it's nice and easy. But this one is a composite function, so I have to use the chain rule. So this one, no, I guess this wouldn't be f. This would be f. So this one's going to be kx is going to be x squared. So k prime x is going to be 2x. And then bx is my inside function, so that's 4x squared minus 3. So b prime is 8x. All right. So if this is my, see, it's all labeled f of x, so I'm all screwed up now. F of x, g of x. So if I'm looking for the derivative of g of x, which is my composite function, it's going to be 2 times 4x squared minus 3 times 8x.
I guess you could go.
And that's a monomial. You could multiply it in if you wanted to. It might be helpful to multiply it in because we got to do derivatives one more time. But we're going to get better at this. Okay. So do you guys remember product? Do you guys remember product? So original f, 24x, times by the derivative of g of x, so 16x times 4x squared minus 3, bracket, bracket, plus original g of x times by the derivative of f of x. You okay? All right. So let's go ahead. I think the best thing here to do is I think we're going to actually multiply this through. Yeah. So remember, this was the statement for velocity. This is acceleration. So 24 times 16. 384x squared times 4x squared minus 3 plus, and I've got to expand that, so that's going to be 4x squared minus 3 times 4x squared minus 3 times 24. This is not bad. Because once we do this, it's going to be so much easier to just use our rules.
Oh, and then just fun and games.
What's fun and games?
When we get to use rules.
True story. Okay, holy Hannah, did you guys get the same numbers as I did? Maybe sort of? Take a minute? Okay. I'm dangerously not using an erasable pen, so. I gotta combine like terms now. That's what I got for acceleration. Okay? Everybody agree with me, or are you just copying what I have?
Until we went to the thousands, I was like doing it on my own. But then once we went to the thousands, I'm like, okay.
Okay, the first one we did, we were in the thousands, so you didn't do any?
No, well, right after we hit the thousands, I gave up.
Okay, so the nice thing about doing that, it was a little bit of math, but really it was just multiplying and exponent rules, right? We should be comfortable enough. It's long, but it's not terrible. And so now we're gonna do the jerk motion. So we're gonna do the third level derivative. So 3 prime symbols. And the nice thing about this is we can just use basic rules. There's no composite functions here. There's no chain rule to be had. So we're just gonna go ahead and do the quick rules. So it's gonna be 4 times 1920 gives me 7,680 x cubed minus 1728 times 2 minus 3,456 x
And then the 26, 216 just.
goes away. Yeah, doesn't go dead, it just goes away because it doesn't have, the derivative of it is 0. So we're just not gonna write 0. Okay, so that's that. It's not great, but it happens. So this is what I'm thinking. I'm away on, oh, I guess I can stop the video. I don't have to show you on the video.